hypothesis tests around proportions. So 12.22 starts by saying 11% of the products produced by an industrial process fail to conform to specifications. And that's pretty lame. 11% when you're a company and you're trying to build something and you have failure after failure like this, you got to do something. And so they tweaked their process in an attempt to have less failures. And this is what they had. So it used to be 11% of products failed. And then they tweaked it. So then after changing a process, they found that 16 of the next 300 products failed. And so what we want to know is this a big enough change for us to believe that that they're doing things right, that they change things in a way that that makes the process better, right? That they're actually improving their manufacturing processes. So this is our 4-step problem, and I'm just gonna go through it rapid fire and unmute yourself and chime in if you have questions along the way. So our step 1 is simply to establish what's going on here, right? So what's my population? What's my parameter? What's my null hypothesis? My alternative hypothesis? And at what significance level am I going to be convinced that there's real change occurring? So the population is going to be all products produced. P-R-O, produced. And my parameter is the true proportion. We're now talking about proportion. That's P instead of mu, the true proportion of failures. My null hypothesis is that even though I change the way I'm doing things, I still have this 11% failure rate. The alternative hypothesis is that I've actually improved things and that my failure rate is less than 11%. And what's going to convince me that we've actually made a positive change? Well, a result that would happen randomly less than 5% of the time. That's my significance level right there. So we see that step 1 is exactly the same as it has been for the past chapter and a half of our work. The only tweak is that we're now talking about proportion and P instead of our population mean mu. So P instead of mu, only difference there. So as far as conditions are concerned, again, we're looking at the same exact stuff as we were for when we were talking about the mean. We still need a simple random sample. We still need to prove normality, and we still need to show that we have independence. For this one, they are just taking the first 300 of the products they're producing now that they've made some tweaks to the process. It's not a simple random sample, so we have to assume that it acts as one. For normality in a proportion problem, we don't have the central limit theorem to help us out, but we have to show that the sample size is big enough that normality is a non-issue. So if it satisfies n times my hypothesized proportion, that's this guy right here, that 11%, if that's greater or equal to 10, and at the same time n times the complement of that is also greater or equal to 10, then we're good to go. I'm going to sub some numbers in and show that this is true. So my sample size is huge. A sample size of 300 is pretty much going to get us there, regardless of what my proportion is. 11% times 300 is 33, so we're good to go there. If I did 300 times its complement, 89%, that gives us, what would that be? That would be 267, so that one is definitely good to go. So it looks like we've got normality. Big sample size really is what it's all about when it comes to proportion problems. Independence, all products has to be greater or equal to 10 times my sample size. So I would like to think if a company is producing products that 3,000 is a pretty small number as far as production. Even if we're making big things like cars, 3,000 is a pretty small number for production. So I think we're good to go there. So you see that conditions, again, we're looking for the same three items, but the way we do normality has changed just a little bit. All right, now calculations is just variation on our theme. So we are going to go to step 3, our calculations. Calculations work like this. We're going to figure out a z-score. Proportion is back to z, so we're on table A. We've shown that we've got normality, so we're good to go there. Z is equal to my sample mean, p hat. Let's talk about that real quick off to the side. P hat, the sample proportion rather, not sample mean, is x over n. That is to say 16 over 300. 16 over 300. So that makes my p hat 0.053 minus my hypothesized mean, p sub naught, divided by the standard deviation of my estimate. That's my hypothesized mean times its complement over the sample size. Let's drop in some numbers. 0.053 minus my 11% divided by the 11% times its complement over 300. Now this value here, this huge sample size, is going to do a lot of work for us. The result that we're going to get here is going to be, it's going to be pretty impressive. So what is z? Well, in order to do this problem, you could drop all of this into your calculator, but I always tend to screw up my order of operations. Don't put parentheses in the right spot and get a weird answer. So I'm going to use my calculator here. I'm going to hit this. Well, let's do the zoom, real close zoom. Oh, there it is. Okay, so I'm going to hit the stat button. There it is. And then I'm going to arrow over to tests. And, oh man, hard to do. There, okay. Arrow over to tests and down to a one proportion z-test right there. It's number 5. And then in everything goes. My null hypothesis of 0.11, my number of successes of 16, my sample size of 300, and then my alternative hypothesis was that my new proportion is less than my old proportion. So it's that middle guy right there. Go down to calculate. And there we go. We see that the z-score is negative 3.1, I'm going to round 4, which is way, way, way far away from the mean. We see the p-value is 8.5, which makes me pump the brakes a little bit, and we'll talk about that. So z is negative 3.14. And a p-value, it says 8.5, which makes me go, what? Hold on a minute. And if I look a little bit closer, I actually see that it says e to the negative 4, which actually means it's in scientific notation, which, thank goodness, because you can never have a probability bigger than 1, right? So, so this is actually 0.00085. Wicked small, super small probability. So that's going to make our next step, our conclusion step, way, way easy. Let's finish strong here. Step 4. Make sure this is dry. Okay, step 4. Conclusion. We've got to have evidence. We've got to make a choice, and then we have to frame that choice in the context of the problem. So our evidence was overwhelming. We had a p-value of 0.0008, which is way less than our alpha of 0.05, which makes the choice easy. We definitely reject the null hypothesis. And in context, that means that it seems the probability of product failure is less. The probability of product failure is less, so there you go. Did the company improve its processes? The answer is definitely yes. They most certainly improved. But part 2 of this question really gets at the whole story. So a hypothesis is good for saying, was there a change? Yes or no? Did something different occur? And so here we said, yes, the company is producing less failures. What we need to get a little bit more information is a confidence interval. A confidence interval tells us where is our new probability. And so question 2 on the quiz says, make a confidence interval and interpret that. So when it says make a confidence interval and interpret, we can skip step 1, we can skip step 2. We don't have to set up our population and parameter. We already did that when we were talking about our hypothesis test. We don't have to establish, is it a simple random sample, normal, or independent? We've already done that, again, with first problem. So we can jump right to the calculation. And let me remind you what that is, because, it's been a while. So we actually did this before we left school, and it looks like this. A confidence interval is p hat, so this is my sample standard deviation, plus or minus z star times the standard deviation of the sample. So that's this guy. Notice that we're using p hats rather than p sub naughts. All right, I'm just going to dump some numbers in here and we'll run the calculation again on my calculator because a lot of button pushing, a lot of opportunities to make mistakes otherwise. So p hat was 0.053. That was my sample failure rate. Plus or minus z star. Z star is how many standard deviations up and down we need to be in order to capture a certain percentage of the population. Now, the problem prompts us to create a 95% confidence interval, which means I could go to my green sheet and at the bottom on table C, I would look up the 95% right there and it says 1.96. So 1.96 standard deviations above and below the mean gives me a 95% confidence interval. Times the square root of 0.053 and its complement, 0.947, over the sample size, that big 300, and we get, using my calculator, again it's stat, over to tests, down, this time all the way down to a z interval, and we get these values. 0.028 and 0.079. So I'll erase all this computation stuff and we'll talk about what these guys, those numbers, mean. Again, in the context of the problem. So this is, we just created my confidence interval, and now we're going to interpret the confidence interval. All right, so this should be very, very familiar, or at least cause some sort of traumatic flashbacks. I am 95% confident that the true proportion, again we're talking about the population proportion, big P, of failures is between, and this is where I'm going to use my values right here. I'm going to convert them to percent so they're a little bit more user friendly. So 2.8 and 7.9%. So we see that they have indeed improved from their 11% failure rate. There's, about a 5% range where we think they might be. We're really confident that they're in here. If we want to get more specific, we could be less confident or have a larger sample size. But that really is the 15-minute version of that entire practice problem. And the quiz, the 12.2 quiz, is pretty much this problem with different numbers. How's everyone doing? Any questions? Awesome. Sweet. Well, good deal. I will count this as attendance for the week as well. You're showing up here, so we're good to go in that regard as well. But if you get into the quiz and are having difficulties, feel free just to shoot me a comment via Google Classroom, and I try to respond as quickly as I possibly can. So we're good to go. Thanks, guys. No worries. Take care.
So, those two girls.
3.